Alright, we have two more examples here for the remainder of this lesson. These two examples are asking you to find the zeros and graph, so putting everything together. In this particular problem, notice that my polynomial is already factored, which usually is a very good sign. Although, how am I supposed to find the degree if it's already factored? Remember, we just take the first term and multiplicity of each of the factors and multiply them. 3x times x squared times x is going to be 3x to the fourth plus a whole bunch of other junk, but I really don't care what they are. All I care about is that I have a degree of 4, which is even, and a leading coefficient of 3, which is positive, meaning my end behavior is up and up. On the possible rational zeros, I have non-applicable because I already have it factored. Factor form, again, not applicable. I already have it factored. This is usually the hard step, which is actually already done for us. So I wouldn't be asking those two steps on this particular problem. I just wanted to mention that we wouldn't be needing those two steps because it's already factored. So I can tell you the multiplicity right now. I set each of the factors equal to 0. The first one might be the hardest one. 3x is negative 6. Looks like I have 0 at negative 2. I've also got a 0 at positive 1, but notice that has a multiplicity of 2. And I've also got a 0 at negative 4. That should be my total 4 zeros that I need, because my degree is 4, so I need 4 zeros. 1, 2, 3, 4. And I do. To get the x-intercepts, I just take my zeros and write them as an ordered pair. And then to find the y-intercept, I evaluate f at 0. And I always go back to my original function. Which in this case happens to be 0 plus x is 6, times 0 minus 1 is negative 1 squared is 1, and 0 plus 4 is 4. When I multiply that all out, f of 0 is 24. So my y-intercept is 0, 24. Now I can take all that information and graph my polynomial function. I'm going to list my zeros, negative 2, 1, and negative 4. I also have a y-intercept of 24. And don't forget that your 0 at 1 is a multiplicity 2, which means it's going to bounce. Looking at my end behavior, I know I'm going to be up and up. Coming from the positive infinity, I need to hit the negative 4. Because the negative 4 doesn't have any multiplicity, or it just has a multiplicity 1, my graph passes through it. Because negative 2 has a multiplicity of 1, again it passes right through it, which is great because then I'm going to hit the 24. I know I have to come back down here and hit the positive 1, which means I have to turn around or bounce because 1 has a multiplicity of 2. And then I meet back up with my end behavior. Notice you always should meet up back with the end behavior so that it matches with your multiplicity in the end behavior. It's kind of a self-checker. And that's all you have to do on that one. It was a little bit easier than most because it was already factored. One last problem for us. F of x equals x to the fourth minus x cubed plus 2x squared minus 4x minus 8. I have a degree of 4, which means I should have 4 zeros. I have a leading coefficient of 1. 4 is even, and the leading coefficient is positive, means up and up for my end behavior. This is not factored yet, so I am going to have to factor that myself. My possible rational zeros are the factors of my constant term, negative 8, over the factors of 1, which was my leading coefficient. So the factors of 8 are 1 and 8, plus or minus 1, plus or minus 8, plus or minus 2, and plus or minus 4, over plus or minus 1. Meaning the possible rational zeros are plus or minus 1 over 1, which is 1, 8 over 1, 2 over 1, and 4 over 1. I really like it when we have a leading coefficient of 1 because then you don't have any fractions in your list of possible rational zeros. Next, I'd like to find the factored form, which means I have to use synthetic division and start guessing. Before I do that, I'm going to take just a minute to do my Descartes' rule of signs. In my f of x, I have one sign change, two sign changes, three sign changes. The last one is not a sign change because it goes from negative to negative. So I have three sign changes of f of x, which tells me that I have 3. 3 minus 2 is 1, so 3 or 1. 1 minus 2 is negative 1, so that doesn't make much sense for being a number of positive real zeros. So I have either 3 or 1 positive real zeros. In order to find the number of negative real zeros, I have to evaluate f at negative x. Some students may consider this to be a lot of work, but it may help us out in the long run. It may not, but we're going to go ahead and try it for today. This is really truly an optional step, and if you don't want to use it, you don't have to, but it may save you some time. So once I've evaluated f of negative x, it looks like I have only one sign change. So one sign change of f of negative x tells me that I only have one possible negative real root. So I either have 1 or 3 positive real roots, and I only have 1 negative. Now because you have a possibility of having positive or negative, the choice is up to you about where you start. For me, I think I'm going to start with the negative numbers, because if I find one negative root, then yay, I'm done. I can't have any more than one. So once I find the one, I'll stop using negatives. So the choice is up to you, but I think we'll go ahead and start with negative. So I'm looking at my list of 8 numbers here, and I'd like one of them to be a negative. And like I said earlier, I'm just pretty lazy. I start with the smallest one, and I'm hoping for the best so I don't have large numbers. So I'm going to start with negative 1. 1 times negative 1 is negative 1. Add down. Positive 2. Add down. Negative 4. Add down to get negative 8. Positive 8. Yay! Hey, look at that. I got it right on the first try, which means negative 1 is a 0. In fact, you can actually go ahead and start putting it in your list. We could also put it in our factored form, because I know x plus 1 has to be a factor. Now, I have more factors here, but I don't know what they are yet. And now I'm going to have to pick another one, because it went from x to the 4th down to x cubed. So actually I still need to keep going, because I need to keep synthetically dividing and factoring in order to get a quadratic remaining. So I'm going to try another one of the possible rational zeros. Although, because I have a negative real zero, I have found the only negative root, or 0. Because I found it, I'm never going to try another negative again. I'm only now going to try positives. So in order to try a positive, I don't know, let's go ahead and from here use a positive 1 and see if that works. 1 times 1 is 1, add down. Multiply, get negative 1, add down. Positive, well, that didn't work, did it? We tried. So I need to try another number. I've tried 1. The next highest number is 2, so I guess I'll go with that one. You could try 8 or 4. I am just going to go ahead and try the smallest one, so I'm going to use, again, the leftover polynomial here, 1, negative 2, 4, and negative 8, and try another number. Instead of 1, I'll use 2. Remember, don't pick any negatives, because you've already found the only negative root we should have. 1 times 2 is 2, add down. 2 times 0 is 0, add down. 4 times 2 is 8, add down, you get a 0. Hey, I got it. That's really good news for us. So that means 2 is a 0. If 2 is a 0, that means x minus 2 is a factor. And now I went from x cubed down to x squared. So my remaining polynomial is x squared plus 4. In order to find that 0, I set it equal to 0. I can't factor it, so I'm just going to leave x squared plus 4. But I can solve using the square root method, so I'm getting x is plus or minus 2i. Do I have all 4 zeros that I was expecting? 1, 2, 3, 4. Yes, I do. Plus 2i and minus 2i are two distinct. Even though you write it as 1, that's just because we're being lazy. Instead of writing 2i, comma, negative 2i, we're just writing plus or minus 2i. Now I can finish out this problem. My x-intercepts are going to be my zeros, comma 0, written as an ordered pair. You could write 2i, comma 0, except that doesn't really make much sense, does it? 2i is not going to be on my real plane, so I'm not going to even bother writing it. My y-intercept is going to be 0, comma something, and we find that by finding f of 0. I like going back to my original function and plugging in 0. 0 to the 4th minus 0 cubed plus 2 times 0 squared minus 4 times 0 minus 8. 0 minus 0 minus 0 minus 0 minus 8 is negative 8. Now I have all the information that was asked for, and now I can graph. I have my zeros at negative 1 and 2. I have 2 more imaginary zeros, but I can't graph that on my real plane. I have a y-intercept at negative 8, and I know my end behavior is up and up. So from my up, I'm going to cross my negative 1 because it has a multiplicity of 1. At some point, I need to cross negative 8 as my y-intercept. Not sure exactly where it turns around. At 2, I'm going to cross my axis, and then I'm going to go up forever. Notice that my end behavior and my zeros matched up, including their multiplicity. Now, there is a possibility here that there may be an extra bump or peak and valley that may not cross the x-axis, and that's a possibility, but we just don't know exactly where that is unless you have some graphing software to see what that looks like. So you can include an extra bump if you really want to, or you can just go ahead and finish that out like that, because we just really don't know what the extra may or may not look like. So that's it for this section. So in this section, we talked about the fundamental theorem of algebra, knowing that we have at least one degree. We have n complex zeros for every function with degree n. We talked about the linear factors, that we have n linear factors for a polynomial of degree n. We also talked about the polynomial functions having complex roots, or zeros, come in pairs of complex conjugates. We talked about the rational zero theorem, which found all the possible rational zeros, which took our possible list of things that we should choose from down to a finite number. And then we also looked at Descartes' rule of signs, which take that list down even farther, looking at the number of positive and the number of negative real zeros. Finally, we put the whole picture together from the last 3 lessons, and we found all of the zeros of any polynomial graph using the possible rational zeros and synthetic division to factor very hard polynomials. Once we factored them, we could find the zeros, the x-intercepts, and graph.